The 2010s marked the start of a groundbreaking era for AI thanks to the rise of deep learning. Among its most powerful tools, convolutional neural networks, or CNNs, which transformed how machines understand images. Let's break down the concept of convolutional neural networks, CNNs, with a simple analogy. Think of analyzing a photograph not all at once, but piece by piece, similar to how a detective might approach a complex scene. The image is divided into smaller sections, and each part is examined in detail to identify edges, shapes, invariants, and textures. One section might reveal part of a face, another a chair leg, and another a window frame. As more pieces are analyzed, a fuller understanding of the overall image begins to emerge. CNNs work the same way. They scan images in small sections, detecting patterns like edges and colors before assembling them into complex objects. The CNN starts by looking at small sections of the image, just like our detective. This process is called convolution. In each section, the CNN tries to detect simple patterns like edges, colors, or textures. It uses something called filters, or kernels, to scan the image. Each filter is like a magnifying glass that highlights a specific feature, like horizontal edges or vertical lines. After detecting these initial patterns, the CNN simplifies the information using a process called pooling. This step reduces the size of the image while keeping only the most important features. Think of it like summarizing. Instead of keeping every tiny detail, you focus on the most crucial parts, like the outlines of objects. The CNN goes through multiple layers, each time combining the simpler patterns from earlier layers into more complex ones. As it moves deeper into the network, it starts to recognize larger and more specific parts of the image, like a whole face or an entire object. In the final layer, the CNN puts everything together and makes a decision about what's in the image. It might say, this is a cat or this is a car, based on all the patterns it recognized. Imagine the CNN is trying to identify if there's a cat in a photo. In the first layers, it detects basic features like edges and colors. In the middle layers, it starts recognizing parts of the cat, like the shape of ears or the texture of fur. And in the final layer, it puts all these parts together and confidently says, yes, this is a cat. Naturally, CNNs aren't just for distinguishing between cats and cars. Within ABBYY products, for example, CNNs are used to classify incoming documents based on their appearance or layout for further processing. CNNs are incredibly powerful for tasks like image recognition, object detection, and even analyzing videos because they're excellent at finding and understanding patterns in visual data. This makes them crucial in a wide range of practical applications. In healthcare, CNNs are used in medical imaging to detect diseases like cancer. IBM's Watson Health, for instance, employs CNNs to analyze radiology images, helping doctors identify tumors with greater accuracy and speed. In the tech industry, CNNs power facial recognition systems, such as those used by Facebook to automatically tag people in photos, and by Apple's Face ID to unlock iPhones securely. CNNs are also critical in the development of self-driving cars. Companies like Tesla and Waymo use CNNs to help vehicles interpret their surroundings, recognizing objects like pedestrians, road signs, and other vehicles to navigate safely. In retail, CNNs are employed in automated checkout systems like Amazon Go stores, where they help identify products in customers' baskets without the need for traditional scanning. These examples truly demonstrate the versatility and immense importance of CNNs in so many modern technologies that rely on visual data processing. From medical diagnostics to our everyday devices, CNNs are quietly revolutionizing how machines see and understand the world around us.